All right, hello everyone, and welcome to lecture 2 of computer architecture. Today we're going to be talking about performance, specifically how we quantify the performance of a computer system. So to start talking about performance, I first want to introduce the notion of clocks. So computers are driven by clocks, and clocks determine when events take place, right? Because a computer is doing a whole bunch of things, and it's important that these things take place in an organized way, take place at the right time. And to ensure that, what we need inside of a computer is we need a clock that ticks and makes sure that events take place at the right time. So a clock cycle is a discrete time interval between two pulses of an oscillator. So there's this clock that's ticking in the computer, and the clock cycle is basically the duration between two pulses of the oscillator that's driving this clock. So for example, if we have a clock, the clock is something like this. The clock, it oscillates like this. It goes up and down, up and down, up and down. So one pulse of this clock cycle, you can see here you have a clock. We call this a clock edge. So this entire pulse of the clock cycle, we call this of the clock. We call this one clock cycle. And usually the way that the computers work is in between edges of the clock cycle. So in between pulses, what we do is we do some work, and then on the clock cycle, we update some data in the computer based on the work that we did throughout the clock cycle. So maybe we, in one of these clock cycles, we read a value from memory, or maybe we performed an add operation. And so what we do is we perform that operation, and then the result of the operation is saved at the end of each clock cycle, so that maybe another operation on the next clock cycle will use that result. So this notion of clocks is very important in discussing the performance of computers. A clock period is the duration of the clock cycle. So we said that a clock cycle is the distance from between two pulses of the oscillator. So this whole thing is a clock cycle. The period is the amount of time that a clock cycle takes. The clock rate, or the frequency, is the number of clock cycles per second. So it's basically the inverse of the clock period. So when we say that, for example, the Intel Core i7 has a clock rate of 3.7 gigahertz, what we mean is that this processor executes 3.7 giga or billion cycles every second. And then if you want to find out the clock period, you basically take the inverse of this. So 1 over 3.7 gigahertz is going to be whatever that value is going to be the clock period. Okay. All right. So given what we said about clocks, the question is, if I have two CPUs, one CPU is clocked at 2.4 gigahertz, and another CPU is clocked at 3.8 gigahertz. Which of these two CPUs do you think has better performance? Okay, so some people say that CPU 2, which has 3.8 gigahertz, has better performance because it has higher clock rate. And the answer is this is a trick question. So let me tell you why it's a trick question. Okay, so somebody was saying we need to fix all other factors, and that's a good observation. So let me say why this question is a trick question. And to say that, I want to ask you another question. So which of these two vehicles has better performance, do you think? This car or this bus? Some of you should recognize this bus, by the way. Okay, so this is also a trick question. Which one has better? Some people are saying the bus has better performance. Some people are saying that the car has better performance, and this can actually both of these can be correct answer. The answer is it depends on the performance metric that we care about, right? So when we say performance is a general word. there can be many different performance metrics that we might be interested in. So when we ask which of these vehicles has better performance, or which of these vehicles is better, we need to be careful that we are talking about the same performance metric. So now let me be more specific about what I mean when I say performance. So if we care about minimizing the time that it takes to transport one person from one place to another, so we can call this the execution time. In this case, which of these vehicles has better performance? Right, the car, exactly. So the car has better performance if my performance metric is execution time. Now, if my performance metric is throughput, so if we care about maximizing the number of people that we can transport in a certain amount of time, so in other words, throughput, then which of these has better performance? Right, the bus, exactly, because the bus can take maybe 20 people at the same time, but if I wanted to take 20 people in the car, I would probably have to make around 4 or 5 trips. So that's likely going to take more time in total. So if I cared about throughput, then the bus in this case would have better performance. What if my performance metric was energy efficiency? So if we care about minimizing the energy the energy that we need to spend in order for us to transport one person from one place to another, which of these will be more energy efficient, the car or the bus? Right, so some people are saying the car, some people are saying the bus. It depends, actually. It depends on how many people I have. This one is a little bit more complicated to estimate. Most likely, the bus is going to be more energy efficient. But we even have a vehicle that's more energy efficient than both of these, and that would be a bike, right? So if I cared about energy efficiency, I probably shouldn't use either a car or a bus. I should probably just have people ride bikes. Okay. So then let's go back to our original question. Which of these has better execution? So let me go back to our original question. Which has better performance? I'm going to be more specific now. So which of these two processors has better execution time? So execution time, by execution time, I mean the time that it takes to perform one task. So which of these has better execution time? Okay, so people are saying CPU2, and it makes sense for CPU2 to have better execution time because it has higher clock rate. But the answer is that this is still a trick question. This is still a trick question, and I'll show you why. So when we say execution time, what we typically mean is the number of seconds that it takes to execute a program. So the time that it takes to perform some task, to execute some program. And execution time can be broken into two factors. It can be broken into the number of instructions in a program times the number of seconds it takes to execute to execute an instruction. And this portion, the seconds per instruction, can further be broken down into the number of clock cycles that we need to execute an instruction and the number of seconds that it takes to execute a clock cycle. This first factor over here, instructions per program, we refer to this as the instruction count. The second factor, clock cycles per instruction, we call this we have an acronym for this, we call it the CPI. So whenever you hear me say CPI, I'm referring to the number of clock cycles it takes to execute an instruction, clock cycles per instruction. And this here, seconds per clock cycle, this is the clock period, right? Remember, we said that the duration of a clock cycle is called the period, and this is basically the inverse of the clock rate. So it's the inverse of the frequency. Okay, and the given I gave you on the previous slide was CPU1 had 2.4 was clocked at 2.4 gigahertz, and CPU2 was clocked at 3.8 gigahertz. So what this tells me is the clock rate, but I haven't really given you any information about the CPI or the instruction count. So we cannot decide based on just the clock rate which of these CPUs will have better execution time at executing some program. or on average. Okay, is that clear to everyone? Does anyone have any questions? Okay, great. So having broken down execution time into these three factors, instruction count, CPI, and clock rate, as computer architects, when we go about optimizing CPUs, when we go about reducing the execution time that a CPU takes to perform some task, this often involves tackling all three of these factors. So different design decisions we make may reduce one or two or three of these different factors. Now, for a very long time, we've been getting a lot of improvements in circuits technology. And I spoke about this briefly last time, but I've said that, we've had these massive improvements in the devices layer. We've had massive improvements in circuits technology that led us to be able to drive computers at higher and higher clock rates. And by driving computers at higher and higher clock rates, what this meant is that without changing anything about the computer, by simply making it run at a faster clock rate, we were improving the execution times of computers. And this meant that if you wrote a program to run on some computer, when another generation of this computer comes out with a faster clock rate, you automatically got faster execution time without you having to change anything, without the programmer having to change anything about their software, and without computer architects having to change anything about the architecture of the CPU. And because this improvement in clock rate gave us better performance without us having to change our software or our architecture, what this trend was called is the free lunch. It was free lunch because programmers and computer architects got better performance for free. Yes, by improving the clock rate, what I mean by that is reducing the number of seconds per clock cycle. In other words, increasing the frequency of the clock in the processor. Okay, so let's take a look at a little bit of the history that involves this improvement in the clock rate that we've seen over the past decade. So some of you are probably familiar with Moore's law. So Moore's law, it's not actually a law, it's more of an observation or a prediction. And it was a prediction made by Gordon Moore, who was one of the co-founders of Intel. And Moore's law predicted that the number of transistors per unit area would double every 18 to 24 months. So around a year and a half to 2 years. Okay, and this was a prediction that Gordon Moore did, very early on, maybe in the 70s, and he didn't expect it to. The prediction was not intended to be forever. It was intended to be, for a few years. But actually, this prediction held out quite steadily, and since the 1970s, for quite a while, we've seen a trend in the number of transistors doubling every 18 to 24 months. This trend has saturated a little bit recently, but for a long time, what we've been seeing is we've been getting double the number of transistors every year and a half to 2 years since the 1970s up until kind of early on, before this trend started to slow down. Okay, but I was speaking about frequency before. I wasn't speaking about transistors. But the good news is that when transistors get smaller, here we're doubling transistors per unit area. So the good news is that when transistors get smaller, what that means is that we can switch them on and off faster, because something that is smaller is easier to switch on and off in a circuit. And that's why this improvement in the size of the transistors and how many transistors have per unit area was coupled with an improvement in frequency. Okay, so the frequency followed the same trend because smaller transistors can be switched faster. However, what we saw is that around 2005, there was a stagnation in frequency. So in other words, there was no more free lunch. Okay, And the question is, so we were getting more transistors, the transistors kept getting smaller, but the frequency at which we were switching these transistors could no longer be increased. That's why around 2005, we stopped getting improvements in frequency. And the question is why? Why do you think, or let's see if anybody already knows, why do you think that even though the transistors kept getting smaller, we couldn't switch them on and off faster? And does anyone happen to already know, or maybe somebody mentioned this to you in an earlier course? Okay, well, the reason is...
Sir?
Yes?
We are saying that the area that's covering the transistor is getting smaller, because the transistors are getting smaller.
Right, the transistors are getting smaller and smaller.
Yeah.
That means in the same area, we can fit more transistors, exactly.
We can fit in more transistors. But we are having more transistors than before.
Right.
So the difference, it's for the benefits of the frequency.
So there's two benefits. One benefit is that we get two benefits from having smaller transistors. One of them is that we can have more of them in the same unit area. The other benefit is because these transistors are smaller, we can switch them on and off faster, and that benefits the frequency.
Okay, got it.
Okay, great. The problem is that even though the transistors kept getting smaller and smaller, around 2005 we were no longer able to switch these transistors on and off faster, and the reason is the power wall. Okay, the reason is the power wall. The reason we were no longer able to switch transistors on and off more quickly is because of power. And let's see what I mean by power. So power, in other words, power is basically the energy consumed per unit time inside of a processor. So power is proportional to three things. It's proportional to capacitance, the capacitance in the circuit. It's proportional to voltage, and it's actually proportional to the square of the voltage. So voltage has a very high impact on power. And it's also proportional to frequency. And because of this, as you can see, when we increase frequency, what that does is that it increases the power consumed in the circuit. Okay, so increasing frequency increases power, which dissipates more heat. And when the processor is consuming more power, what happens to this power? We use this power to switch on and off these devices, but then what happens is that this power consumption results in heat dissipation. And what we need to do is, with all this heat, is we need to cool it. And that's why we have fans in our computers, in order for us, in these fans, whenever we feel that the computer heats up, there's a fan that turns on and starts cooling the computer. So the problem is that we cannot indefinitely increase power because there's a limit to how much cooling we can do, right? So if I increase power too much, my fan that's in my laptop or in my desktop will no longer be able to cool the chip fast enough, and the chip will begin to melt. Okay, so this is why, even though the transistors are smaller and we can hypothetically switch them faster, we can't do it because we cannot cool the chip fast enough to absorb all the dissipated power. Now, the way that circuit designers have dealt with this phenomena in the past is that we increased the frequency of the transistors, but because they are smaller, we were also able to decrease the voltage that is used in the circuit for these transistors. And by increasing the frequency but decreasing the voltage, this somehow offsets the increase in power, so that it is not as pronounced as the increase in frequency. So historically, the increase in power was partially compensated for by a decrease in voltage. And the decrease in voltage was also enabled by the decrease in transistor size. And that's why over the past 20 years, we've seen 1,000 times increase in frequency, but only a 30 times increase in power, and that is because we have a less decrease. We have a decrease in voltage to compensate for that. Now the problem is we were able to compensate for the increase. We were able to partially compensate for the increase in frequency by decreasing voltage, and that led us to be able to increase power, but not as much as the frequency was increasing. However, now we face another problem, which is that today we can no longer decrease the voltage. The reason we can't decrease the voltage is because when the voltage gets too low, these transistor devices become less reliable. Operating these transistors at low voltage makes them less reliable. So we can no longer decrease the voltage. And because we can no longer decrease the voltage, we can no longer improve frequency. And the reason is that since we can't decrease the voltage, we also can't increase the power because we've reached the limits of how much we can cool these CPUs. So because we cannot decrease voltage and we cannot increase power, we can no longer increase the frequency. Okay? And if we go back to the graph that we originally saw, this stagnation in frequency, it's very clear that the stagnation in frequency is correlated with a stagnation in power consumption. Okay? But there's still good news. The good news is that this stagnation in frequency, which is correlated with stagnation in power, even though we face this problem, we are still getting more transistors, which means that we can no longer have a free lunch. We no longer have free improvement in speed up, with free speed ups from the improvement in frequency. But we're still getting more transistors, which means that we can take advantage of the fact that we have more transistors to try and get improvements in performance from somewhere else. And let's see what we can do with these additional transistors. So the question is, these additional transistors that we're getting, where should we invest them? And there's different processors, and take different approaches in how to invest these transistors to continue to improve performance, even though we're not getting better frequency. One way is to increase the number of cores in our processor. And in fact, after 2005, when we hit the power wall and we were no longer able to improve frequency, what happened was a lot of processor vendors started to move to having multiple cores in the system. And increasing the number of cores, what does increasing the number of cores improve? Does it improve execution time, or does it improve throughput? If I take these transistors and I use them to add more cores into my CPU, so rather than having one CPU, I have multiple CPUs on the system. Yes, exactly. It improves my throughput. Another thing that we could do is we can take these transistors and make the cores more advanced, and we'll talk throughout this course about ways that we can make cores more advanced. So if we do that, in this case we would be improving execution time. So here, what we take one core and we kind of give it, add to it different features that enable us to execute things quicker. And as you can see here, when we design processors, there's a trade-off between execution time and throughput, right? So just like when you have a car and a bus, right? You can either, if I have a certain limited amount of materials, I have, limited amount of metal, I have limited amount of, gasoline. I can use these materials to build a car, or I can use them to, build a bus. I can use them to make my engine stronger so that I can have less execution time, or I can use these materials to add more seats to my vehicle so that I can have better throughput. So just like in vehicle design, you have trade-off between execution time and throughput. Same thing with processor design. There's a trade-off between execution time and throughput. So if we go back to this breakdown over here, we said that for the longest time we were getting improvements in clock rate, which led to the improvements in execution time for free, but this stopped. So now, in order for us to continue getting improvements in execution time, we have to turn our attention to these other two factors. And in fact, even before the clock rate stopped improving, computer architects were looking at how to improve these two factors anyways. But these became more and more important when execution time, when clock rate could no longer be improved. So computer architects, if you look at CPI, computer architects have developed a wide variety of techniques for improving CPI. In other words, improving how many instructions we can execute in every clock cycle. And I'll briefly mention some techniques for reducing CPI that are common in processors. One of them is pipelining, and we will be discussing pipelining in the third part of this course in chapter 4. Another one is caching, so building caches to store data close by that is frequently used. And we will be discussing caching in chapter 5. Another technique is called out-of-order execution, where we take instructions that are not dependent on each other and try to execute them out of order so that we can execute more instructions at the same time. And unfortunately, we won't be covering this technique in this course, but maybe we might introduce an advanced course where we go into these techniques. Another one is speculative execution, where we kind of somehow ahead of time guess what the computer might do in the future and start doing it before it actually does it. And then if it turns out that our guess is incorrect, we go back and do what it was supposed to do. And again, this is not something that we will cover in this course, but it's good to be aware of it. So these are techniques for reducing the CPI. And then finally, the third factor, which is instruction count. To reduce the instructions per program, to reduce the number of instructions per program, there's actually two players that go into this. The first player is the software. So along with improvements in computer architecture, we've also been getting improvements in compilers. So compilers are becoming better at optimizing code, and of course, in algorithms. So the primary way to reduce the instructions per program in your program is to use lower complexity algorithms and compiler optimization. So software is very important. However, computer architecture also plays an important role in reducing the number of instructions per program. So for example, I could design my instructions in a way where they could be very verbose, where I need many instructions to accomplish one task, or I could design my instructions in a way where I need very few instructions to accomplish one task. Okay, and this is a trade-off that computer architects make. Another thing that can be done is that, and this is a very popular trend. Processors, if there are common operations that are performed, what processors could do is they could provide a single instruction that does this operation in hardware instead of software. So, for example, things mathematical computations like sine and cosine and logarithm. These computations, if you were to do these in software using just multiply and add, you would need to do some kind of Taylor expansion, and that would be very expensive to do all those multiplies and adds. But another possibility is for the hardware to provide some kind of hardware accelerator that just does a sine operation in hardware rather than doing it in software using many multiplies and adds that take many cycles. So this is one example of how computer architecture can be leveraged to improve instruction count. Does anybody have any questions so far?
Yes, sir. It's about the clock rate.
Yeah, go ahead.
Okay, let's say a program takes 3 seconds, and these 3 seconds have done in 4 cycles, but not the clock rate is an average. And each clock cycle is will take time depending on the instructions that it takes.
So the clock rate is not an average. The clock rate is fixed, right? The CPU, a cycle in a CPU will always take the same amount of time because there's an oscillator that's oscillating in the CPU to drive this clock, and this oscillator is regular. Every pulse will take the same amount of time. The average here comes in the CPI. So when I say cycles per instruction here, yes, it's a correct observation that I mean the average number of cycles per instruction, because some instructions might take more cycles than other instructions. And we'll look at this when we cover how to build different circuits in hardware. You'll see how, for example, multiplication might take more cycles than addition takes, for example. Okay, thank you for that question. It's a good question. Okay, so finally, before we end, I want to talk a little bit about some pitfalls that are important to be aware of when designing computers. So the first pitfall, let's say I improve the clock rate of my processor. So a manufacturer comes and they improve the clock rate of the processor. They increase the clock rate, which decreases the duration, decrease the number of seconds per clock cycle. However, because of this decrease in the clock rate, so now every cycle takes less time. Some instructions which used to take one cycle could no longer be executed in one cycle, because the cycle is shorter now. So some instructions that used to take one cycle now need 2 cycles to complete. And what this does is that it increases the CPI. So here, a processor designer has to be careful, because if you improve the clock rate, let's say by 1.5x, and as a result, the CPI increases by 2x, then this improvement in clock rate would actually result in a net decrease in increase in execution time. So a decrease in performance. Okay, so if the increase in the CPI is disproportionate to the decrease in clock rate, the total execution time may actually increase. And that is why it's important that when we come and improve one of these factors of execution time, we need to be aware of how this improvement interacts with other factors. Okay, let me give another example. So let's say instruction count and CPI. So let's say a CPU manufacturer, they create this new instruction that does multiply and add in a single instruction. And this is very common. You guys have probably taken math to 18, and you probably know that all these matrix operations, these are essentially, you multiply and you add, multiply and you add. So it's very common for applications to do a multiply operation followed by an add operation. So many CPU manufacturers have a support for an instruction which is a fused multiply add, where they do multiply and add in one instruction. And the advantage of this is that it reduces instruction count, because rather than doing multiply and then doing add, we can do multiply add in one instruction. So this decreases the instruction count in our program. However, it's important to be careful here, because if my add instruction takes 4 cycles and my multiply instruction takes 8 cycles, and then my fuse multiply and add instruction takes 12 cycles, then I haven't really improved execution time, right? Because the instruction count will go down, but then the CPI will go up, and the net improvement in execution time is going to be the same. So this optimization of doing fuse, multiply, and add, which many processors do, this optimization is only useful if the fuse, multiply, add instruction is going to take fewer cycles than doing the add operation alone and the multiply operation alone. Okay, so this is another pitfall to be aware of when reasoning about how these different factors that go into execution time interact. Okay. And with that, this is the end of today's lecture on performance. If you would like to read more about the material we covered today, you can refer to the textbook, in particular sections 1.6 and 1.7. Okay. Does anybody have any questions before we end? Oh, someone's asking about the chapter. So 1.6 means chapter 1, section 6 inside of chapter 1. So section 1.6. Okay, if there are no questions, then that's all for today, and I will see you next time.